Today's focus is going to be on the atom and the subatomic particles that we find within the atom. So I'm going to start by listing the symbols for each of those subatomic particles. So for a proton, we're going to do P+. And this is because a proton has a +1 charge. Neutron is going to be N with a superscript of 0. And again, that gives us insight into the charge. The charge on a neutron is 0. So when I think of neutron, I like to use the NEUT to remind me that neutrons are neutral. They don't have a charge. Their charge is 0. Electrons have a -1 charge, so they're commonly symbolized with an E-, and we'll do a -1 over here. The masses are also important. Protons and neutrons are located in the nucleus, and they both have a mass of 1 AMU. Electrons do have mass, but the mass of the electron is so much smaller compared to the proton or the neutron. So in terms of AMU, since it's so much smaller, we say that the electron has 0 AMU. And I keep on saying, oh, AMU. AMU stands for atomic mass unit. So what happened is we have such small subatomic particles, right? The AMU itself, its conversion factor is 1.66 times 10 to the -27 kilograms. So you can kind of think of it as a new unit that was defined to give some sense to the masses that we were dealing with. Because they were on such a small scale, we couldn't easily use things like kilograms or grams. But the AMU is on the right scale, right? It's easy to say, oh, a proton is just 1 AMU. You don't want to always have to repeat all this. So just is a unit that reflects the appropriate scale of the mass of the proton, neutron, and electron. It was defined by taking carbon-12, which is a specific isotope of carbon. We're going to talk a little bit about isotopes too in this packet. But carbon-12, they took one of those and they split it theoretically into 12 pieces, and they said, well, that's 1/12 of a carbon-12 is 1 AMU. And then 1 AMU is also defined as being the mass of 1 nucleon. And you could almost probably guess what is a nucleon. Well, a nucleon then is going to be a proton or a neutron. And they're called nucleons because they're in the nucleus of the atom. What you're looking at here is known as the Bohr model of the atom. And I did label it as an old school model because we now know that the atom doesn't really look like this. However, we're going to start here because it's a simplified version. I'll point out some of the issues, and honestly, there are a lot of correct features to the Bohr model that can really help us understand bigger concepts in chemistry. So first thing, we have these electrons on the outside, and we know that they're electrons because they're negatively charged. They have those little negative signs associated with them. Couple things about the electrons. First off, you might notice that they're a lot smaller than the protons and the neutrons in the nucleus. And we did discuss that previously, right? Electrons have a mass of 0 AMU, while these things in the nucleus, the nucleons, actually have masses of 1 AMU each. So it's appropriate that they're a lot smaller. So the electrons are so small and they have such negligible mass that a lot of times you'll hear chemists describe the area around the nucleus. So all of this area, which basically has no mass, is oftentimes called the electron cloud. I love this term. You'll hear me reference the electron cloud a lot. And another reason why this description works, besides the fact that clouds are lightweight and electrons have negligible mass, is that we don't really know where the electron is. So in this diagram, what's really fundamentally wrong with it is that the electrons are going around in circles around the nucleus. It's like planets around the sun. We now know that the electrons occupy orbitals, much larger spaces, and they can move anywhere they want within their orbitals. Just think of this big cloudy area with zero mass, and somewhere within that cloud, you're going to find the electrons. Next thing to know about are the protons and the neutrons. And this is where all the mass of an atom comes from. So if you look on your periodic table, I'll flip to page 2 for just a second. So if you look on your periodic table, you're going to see a number underneath the name usually, and this is known as the mass, the atomic mass. So this atomic mass is due to the protons and the neutrons of carbon. It doesn't have anything to do with carbon's electrons. And then the other thing, which is so insane, is that the electron cloud is this huge area, and then in the middle, you have this tiny nucleus, and the majority, most of the mass, is located within that nucleus, like 99.9% of it. And on this diagram, I'm sure you're starting to put the pieces together. The ones that I colored in yellow are neutrons. And I know that because they don't have a charge written on them. And then in this purple pink color, there was positive charges on those spheres. Those spheres represent our protons because they're positive. The other thing you might be noticing as you're looking at this model of an atom is it has 6 electrons and 6 protons. And you can use the number of protons to identify your atom. So use your protons to identify your atom. You can go to your periodic table, or it just happens to be the same one on page 2. You can look it up, and this big number 6 is known as the atomic number, and that is equal to the number of protons. And it also gives the atom its identity. Like, you cannot change, under most circumstances, you cannot change the number of protons in an atom. So the different atoms of carbon might have slightly different atomic masses, but if it's carbon, it's always gonna have 6 protons. Couple more things to go over. Well, we want to look at this idea of a valence electron. And a valence electron is an outer electron. Valence means like outside. And so on our model, we call the different layers on this particular representation, we call them shells. So this is your first shell. And for the first shell, we say n equals 1, lowercase n. Now we have the second shell. And that's where these 4 electrons are located, the ones on the outside. So on your second shell, n equals 2, that's going to be your valence shell. Why is this important? Who cares? The reactions that occur, the molecules that form, the compounds that form, that's due to our interactions with our valence electrons. The stuff in the middle, the core electrons, they don't do anything. They're just there and all the actions on the outside. How do you determine how many valence electrons an atom has? And this is really important because the number of valence electrons can allow us to predict the behavior of the atom, what kind of compounds it's going to form. We're going to use, in this class, we're going to use the A group number. So if you go to page 3, let's start labeling it. The periodic table is chock full of information. It's mind-blowing. It's almost like the world's best cheat sheet. There's so much information that you can pull off of a periodic table, and every time you take a chemistry test, they always give you a periodic table. So the A classification is not really official anymore. They phased it out, but I love it so much that I still teach it and use it. And you see it on all their periodic tables. So we have 1A, 2A, all the way on the left of your periodic table. And then in the middle of the periodic table, we skip that part. Then we come over here. We're going to do 3A, 4A, 5A, 6A, 7A, and the last column is 8A. So the columns on a periodic table are known as groups. And I usually abbreviate group with GRP. And the number, the group number, if we use the A system, tells us the number of valence electrons. So all of the elements in this first column in group 1 have 1 valence electron. Such good information. It's good to know because they all have 1 valence electron, they're all going to act very similarly. And then we have group 2, so on and so forth. I'm just going to circle the number out front, the group number, because that's the number of valence electrons. In addition, I briefly mentioned on our picture the shells of the atom. So if we look here, right, we got the first shell, the second shell. That information is also reflected in our periodic table. So the shells kind of loosely correspond to the rows. And we call the rows in the periodic table periods. And thus the name periodic table, right? And so our first row is, we could call it n equals 1. Period 1, we have period 2. And I'll do n equals 3 over here. And so the elements that are in the third row of the periodic table have their valence electrons in the third shell. And then I'm just continuing with the labeling of the periods all the way down to 7. Down here, this is like a cutout of the periodic table, like just to save space. So our group 1 metals, they're known as alkali metals. I'm going to write that on our periodic table. ALK, ALI. So group 1A are the alkali metals, super reactive metals. They only have 1 valence electron. And so they're super motivated to lose that 1 valence electron. So what I can tell you about the alkali metals, just by knowing that they have 1 valence electron, they're going to lose that 1 electron and obtain a +1 charge. And they do this very readily. The second group is known as the alkaline earth metals. They're not quite as reactive, but still reactive enough. They have 2 valence electrons. So again, they're going to be motivated to lose those 2 valence electrons, and they're going to form +2 charges. In the middle of the periodic table, we have what's known as the transition metals. They're all over the place with their charges. So I'm not going to write +1 or +2 like I did over here. And then, as I was explaining before, there's this piece that's cut out. So we can call that the inner transition metals. This is where it starts getting more predictable again as we move to the right side of the periodic table. So starting at group 5A, we can predict the charges again. So for 5A, we're going to do a -3 charge. 6A, we're going to have a -2 charge. And 7A is going to have a -1 charge. When you have a negative charge, that means that the atom gained extra electrons. When you have a positive charge, like on the left side of the periodic table, that means they lost electrons. Sometimes I think of losers as being on the left. For group 8A, these are known as our noble gases. And they have no reactivity. They basically don't react with anything. That's because they have the perfect number of electrons. Everybody wants to have 8 electrons, and so they're not going to gain or lose. They just stay at 0, a charge of 0. And then as we move to group 7, since everybody wants to have 8, right? So all group 7 has to do is gain 1 more electron to look like the noble gases. They're so close. So we have a very reactive group in group 7. They're known as the halogens. But they're super reactive because they're almost there. If they just gain 1 more electron, they're going to look like nobility. So we're on page 2. Let's finish filling this out. We had the atomic number, which I stated was equal to the number of protons. The atomic number is also equal to the number of electrons in a neutral atom. So on the periodic table, we labeled charges. Those would not be neutral atoms. But typically we're going to assume, especially with these earlier exercises, that we're dealing with neutral atoms. So the number of protons and the number of electrons will be equal. Here, there's always letters to represent each element. And these are known as elemental symbols. Really clutch on elemental symbols. The first letter has to be capital, and the second letter has to be lowercase. Reason being, I just wrote the elemental symbol for cobalt. It's a metal. However, if I didn't pay attention to the capital and the lowercase, I don't know, just wrote them both as capital, then this would be carbon and this would be oxygen. And instead of talking about cobalt, we would be talking about carbon monoxide. A couple more things here. We have the name of our element, and then we have our atomic mass. So the atomic mass is equal to the number of protons plus the number of neutrons. And since you already know that carbon has 6 protons because of the atomic number, then you're like, well, it must have 6 neutrons, because then we'd have 6 plus 6 getting us to the value of 12. Let's go through some more examples like that. So one of the expectations early on in any chemistry course is that you can fill out a table like this. So you're going to want to have a printout of the periodic table, and I recommend the PubChem one, the first version, while you're still learning the names of the elements. Eventually you're going to have to know the element names, but let's start with this one. And so you're going to, on your worksheet here on page 2, you have atomic number 20, and you're going to come over here and you're like, well, 20 seems to correspond to calcium, because you see the 20 up there. And then they don't give us much more information. They say protons, electrons, and neutrons. Well, because it had an atomic number of 20, we know that it has 20 protons. It's neutral, so the number of protons will equal the number of electrons. The hardest part here, I would say, is estimating the number of neutrons. So calcium has a mass of 40, and I'm not gonna, you can't split a neutron or a proton. This is an average weight that we'll learn how to calculate. So I'm just gonna round it to the closest whole number. You're gonna round the masses to the closest whole number when you're calculating neutrons. So we're gonna do 40 minus 20, because it's got 20 protons, and then we're looking at 20 neutrons in calcium. Classification, well, it's part of the alkaline earth metals, so we know that it's a metal. Let's do one more together. So we have number 14 on our next line. Where's number 14? So we're all the way over here with silicon. So Si, and the number of protons relates back to the atomic number and the number of electrons. So for the number of neutrons, we'll look on our periodic table again, and we have an atomic mass of 28.085. So we're going to round that to the nearest whole number. We're going to do 28. 28 nucleons. Well, 14 of them are protons, and so the remaining mass must be due to neutrons. So I'm going to say that this has 14 neutrons. How do we classify this? So let's go back to our periodic table on page 3 and talk about that a little bit. So obviously, just because of the names here, we got alkali metals, alkaline earth metals, transition metals. We have a whole bunch of metals on the left-hand side of the periodic table. The other thing about all of the metals, they're losers. So I like to say losers on the left. When something loses electrons, it's going to have a positive charge. And so even though I didn't give any specifics about what's going on with our transition metals, we now know that metals will form positive charges when they start losing electrons. Where do the metals end? So you're going to want to draw in a little staircase. It starts there and kind of cuts down. So this staircase is the dividing line between the metals, which form positive charges, and our nonmetals, which form negative charges. So over here in the right hand side, I was about to say in the right hand corner, right? It's just almost like a corner. We have our nonmetals. There is that stair in between, and that stair is occupied by elements that don't exactly look like metals, and they don't exactly look like noble gases. So those are going to be our metals or semi-metals. Examples include the silicon that we were just talking about. And we'll label more in just a minute, but we have a whole bunch of semi-metals located along the stairs here. So germanium and arsenic, antimony, tellurium, I would say, is a semi-metal. There's not complete consensus on all of the semi-metals. So, for instance, if you look up boron, I think most people classify boron as a non-metal. However, there are some scientists out there that will argue, well, it's a semi-metal. Don't stress about it too much. The ones that I have marked here for sure are metalloids. Most scientists will agree about that. But for the rest of them, and as they discover new things or new properties, new behaviors, classification changes slightly. Right here, students always ask me, this is aluminum. And that's definitely a metal, even though it's along this staircase. So don't mark it as a semi-metal. And let me just label. So everything I marked green is a semi-metal. So now we know how to classify the silicon, we can finish up this table. Now we know how to classify silicon, we can finish up this table. I'll call this a metalloid, which is just another term for semi-metal. So here's your completed table from the bottom of page 2. I think the hardest part about this is figuring out the number of neutrons. So for cesium, it has an atomic mass of around 132.9. So I took that value and I rounded it up to 133, and then I subtracted out the 55 protons, which means there's 78 neutrons in the nucleus. And the nucleus is where the majority of the atom's mass is located.